All right. Hello, everyone. It is now 7 o'clock, so I'm going to begin my talk. My name is Andrew Mayo. I am a third-year PhD student at UC Berkeley studying astronomy, and I work on exoplanets, or planets outside of our solar system. In other words, all planets in the universe, except for 8 of them, the ones in our system, are all exoplanets. I work on detecting and characterizing them, and today I'm going to be talking about exoplanets and the search for alien life. So we can start this talk by looking at one of the very first mentions of the possibility of planets orbiting other stars. In 1584, a man named Giordano Bruno said, "In space, there are countless constellations, suns and planets. We see only the suns because they give light. The planets remain invisible, for they are small and dark. There are also numberless Earths circling around their suns." This was a very new and novel idea at the time. Other stars were different from our sun, or so people thought. But, as we now know today, other stars in the night sky are very much like our own sun. And they do, in fact, have planets orbiting them. So this takes us to the first method that I want to talk about today of finding a planet. I'm going to begin by talking about some of the most common ways of finding planets. Then I'm going to talk about some of the most important missions that have been used to find exoplanets. And then finally, I'm going to talk about how we might use these methods and these missions to look for signs of life elsewhere in the universe. The first method that I want to talk about today is called the radial velocity method, also colloquially known sometimes as the wobble method. Essentially, what astronomers do to find a planet with this method is they look at the star itself and look to see whether the star is wobbling back and forth. If anyone is familiar with the Doppler effect, the sound that an ambulance makes as it passes by, sound is compressed and stretched out as the ambulance moves towards and away. In the same way, light from a star gets stretched out and compressed as the star moves towards us and away from us. And we can see a planet pushing and pulling on its host star in this way. And by measuring the size of that wobble, we can measure the mass of the planet and confirm that there is, in fact, a planet there. And in fact, this is the method that was used to find the very first planet orbiting a sun-like star by the name of 51 Pegasi b. It was discovered in 1995, and it was nothing like what we expected. This planet orbited its host star once about every 3 days or 4 days, and it was roughly the size of Jupiter. To put that into context, Mercury orbits our sun once approximately every 80 days. So this planet was very large and very close to its sun. And as a result, it was also very hot, approximately 1,000 degrees Celsius or 1,800 degrees Fahrenheit. Very hot, very large, unlike anything that we've seen in our solar system before. But I'd like to show you what the data looked like, this wobble that I was talking about. Here you can see that over time, the star moved towards observers, and then it moved away from observers, and then back again, back and forth, and back and forth. And that's the effect of the planet pushing and pulling on it. So I talked about how this is a very common method of detecting exoplanets, but it is not, in fact, the most common method. That goes to the transit method. This method is fairly straightforward to understand. As a planet orbits its host star, if the system is edge-on to us, if we happen to be coincidentally in line with the system, we can see that the planet might cross in front of its star and cast a shadow, if you will. A small planet will cast a small shadow. A large planet will cast a large shadow. And by looking at how large that dip in light is from the star, we can measure the size of the planet. Now, I should note that that is not the same as the mass of the planet. If you have a planet made entirely of lead and another planet made entirely of hydrogen, they could be the same size, but very different masses. So by combining these two methods together, if you can look at a planet with both methods, you can determine how large it is and how massive it is, and start to learn about the density of the planet. Is it rocky, like planet Earth, a surface that you can walk on? Or is it puffy and gaseous, more like Jupiter, very large with no discernible surface? I'd also like to show you what the data looks like for the transit method. This is a plot of the very first transiting exoplanets ever found. In 1999, Professor David Charpenow observed these two transits spaced 7 days apart. And you can see that as time progresses, the star is at a uniform brightness, and then the planet starts crossing in front of the star. It gets dimmer and dimmer, and then as the planet crosses in front of the star, it's at a lower level of brightness. And then the planet leaves the face of the star, and then the star continues on its normal brightness. This data down here is an offset, just shifted downward a little, but it's the exact same data that you see above here. And that's how you can determine the size of the exoplanet. But now I'd like to talk about how the transit method has been used most effectively by talking about the Kepler mission. The Kepler mission is arguably the most important mission for the history of exoplanets. It was launched in 2009, and all it did was look at one patch of night sky about the size of your outstretched hand. If you hold your hand all the way out and hold it up to the night sky, it blocks about the same amount of night sky as the Kepler mission. And all it did was look for these transits, these small dips in light from these 100,000 stars, to try and discover as many planets as it could. And what was its mission? Quote, determine the frequency of terrestrial and larger planets in or near the habitable zone of a wide variety of spectral types of stars. Whew. That's a lot of words, and I'm going to break it down a little bit. Basically, the Kepler mission's goal was to look for Earth-like planets and determine how common those planets are in the galaxy more broadly. It was trying to figure out, are Earth-like planets very common or are Earth-like planets very rare? When I say Earth-like, I don't simply mean that the planet is the same size as the Earth. I also want to focus in on this phrase here, habitable zone. The habitable zone is a very important concept when you're talking about exoplanets. Essentially, the habitable zone is the region of space around a star where the planet is not too hot and not too cold. It's sometimes called the Goldilocks zone for obvious reasons. It is a distance from the star where a planet is at the right temperature that you could have liquid water on the surface of the planet. Bring the planet too close, it'll evaporate. Bring the planet too far away, and the water will freeze. But in this zone, you can have liquid water. And we think that's extremely important for life, because on Earth, at least, everywhere we see water, we see life. So we think that water is a prerequisite for life, that you need water if you're going to create life. So I'd now like to talk about another important mission, a follow-up to the Kepler mission. Oh, my apologies. First, I'd like to talk a little about the results of the Kepler mission. There were 4,780 candidates so far that have been discovered over the 4-year lifetime of the mission. Of those exoplanet candidates, we've been able to determine that 2,392 of them are indeed planets. The rest of them we're still sifting out. Some of them may be real planets, some of them may be false signals. But we know at least that about 2,400 are indeed planets. Of those, we found that 361 are in this habitable zone. And out of those 361, we've also determined that 60 are habitable and potentially rocky. So they're small enough that they could also be rocky like the Earth. In other words, our primary lesson from the Kepler mission is that Earth-like planets are everywhere. It doesn't take many systems for us to look at before we find an Earth-like planet. And just as an example, the very nearest star to our sun, Proxima Centauri, has an Earth-like habitable planet orbiting it, Proxima Centauri b. So the nearest star to us has an Earth-like rocky habitable planet, and we think that many, many other stars do as well. So I'd now like to talk about an important follow-up mission to the Kepler mission called K2. The original Kepler mission ran for 4 years, but after about 4 years, unfortunately, it broke. One of the what are called reaction wheels failed, and the mission was no longer able to look at that one patch of sky anymore. However, astronomers were able to come up with a very clever fix. They rebranded the mission as K2, and they found a way to allow it to look at other patches of night sky for about 75 days at a time. So not 4 years, a much shorter time period, but it was able to look at multiple patches of night sky. So that allowed it to look at approximately 20 times more night sky than Kepler was able to. It was also able to find planets around much brighter stars because it was looking at other fields of sky where there were plenty of bright stars than the Kepler field. But as I said before, unfortunately, it couldn't view each field in the night sky for as long, which meant it was only able to find some of the brighter, more obvious candidates. It was able to find planets that transited in front of their host stars more frequently. It was able to find signals that were stronger, but unlike Kepler, it couldn't find very, very long period planets or very small planets, or at least with less success. I now want to talk about the TESS mission. TESS can be sort of seen as being handed the torch of the exoplanet field from Kepler and K2. It was launched in 2018, and it is at the moment doing the most work for a space mission for the field of exoplanets, as Kepler K2 is no longer operating. I'll talk a little bit about how exactly TESS works. So the TESS mission is a space mission. There are 4 very large cameras that cover a large swath of the sky. Here we see one camera, the other 3 are adjacent to it. Over the course of about 1 month, it will look at one patch of sky, and then it will move on to another adjacent patch. It'll continue to look at 12 or 13 patches until it's covered one full half of the night sky in about a year. And then it flips upside down and repeats the process on the other half of the night sky. As a result, it is the first exoplanet mission to look at a majority of the night sky. In this video here, you can see as reference the Kepler field, a very small patch up there, the K2 fields, 20 times more covered night sky here, but the TESS field covering about 85% of the night sky, which is excellent. It allows us to look for a large number of exoplanets which are orbiting very bright or nearby stars. Now, you may have noticed I've mentioned a few times bright stars, and you may be wondering, why do we care about the star being bright? One of the more interesting things that we can do with bright stars involves another mission called JWST, or the James Webb Space Telescope. Now, the James Webb Space Telescope is supposed to launch next year, actually almost exactly a year, about a year and 10 days from today. It's supposed to launch on Halloween of next year. And the James Webb Space Telescope is going to essentially take over for Hubble. The Hubble Space Telescope has been in operation for a long time, and JWST, the James Webb Space Telescope, is going to carry over some of the burden and start being the heavy workhorse for astronomy. It's going to do a lot of excellent astronomy for a lot of different astronomers, but part of the science it's going to do will be for exoplanets specifically. So if we have a bright star where we've found an exoplanet orbiting it, and we have the capabilities that the James Webb Space Telescope are going to be able to give us, then we'll be able to do something called atmospheric characterization, which is basically learning what is in the atmosphere of a planet. How exactly do we do that? So as you can see in this video, we have a cute little graphic of JWST. As the light from a star comes to us, we can split the light up into different wavelengths: red light, green light, blue light, but at other wavelengths as well, outside of the light that we can see, much longer wavelengths and much shorter wavelengths. As the light from a star passes through the atmosphere of a planet, some light makes it through the atmosphere and some light doesn't, and it depends on the wavelength. And that gives us a fingerprint of sorts. We can look at which wavelengths of light get through and which ones don't, and relate those to different types of molecules. Some molecules will block some types of light, other molecules will block other types of light. And by looking at which light we're observing, we can figure out whether one type of molecule or another type of molecule is in the planet's atmosphere, and to what level. Is there a lot of it or just a little bit of it? And that is going to help us look for alien life, because there's a very important thing that astronomers are very interested in called biosignatures, which are signs of life in a planet's atmosphere. One of the most obvious ones is oxygen. On our planet Earth, there's oxygen everywhere. We breathe it all the time, and it is in very high levels of abundance. That's because of life on our planet. Without life on Earth, the amount of oxygen that we would have on the planet would be much, much lower. And so if we can find oxygen on another planet in its atmosphere, that might be a sign of life. Or if we look for other signs, other biosignatures like methane or ozone, we could look for any of those signs. And if we see enough of them, it could tell us that there's life like life on Earth on another planet. Unfortunately, JWST will allow us to look at the atmospheres of larger planets, planets the size of Jupiter or Neptune, very puffy gaseous planets. But it's not going to be able to tell us much about rocky planets like the Earth, which is why the last mission I want to talk about today, LUVOIR, is, in my opinion, one of our best bets at being able to do this. LUVOIR is a proposed mission, which, if accepted, would be launched sometime in the late 2030s. LUVOIR stands for Large Ultraviolet Optical Infrared Telescope. And in the larger version of the proposal, it would be a 15-meter telescope in space. That is enormous, about 50 feet wide, and it is much, much larger than Hubble or the James Webb Space Telescope. If it is accepted as a mission, and if it launches, it would be able to look at the atmospheres of other planets, including rocky planets. And the way you would do this is with a method called direct imaging. Essentially, you can blot out the light from a star in order to look for planets nearby. So what I'm showing you here is an example of what kind of data LUVOIR might be able to collect. If LUVOIR was placed 40 light years away from our system and then made to look back at our solar system, it would be able to see light from Jupiter, light from Venus, and light from Earth. There's that little pale blue dot right there. And all of the light emitted from planet Earth, LUVOIR would be able to look at and analyze the atmosphere of the planet. And I'll show you an example of what that data might look like. This is an example of the spectrum of light that would come from an Earth-like planet if LUVOIR was looking at it. So you can see different wavelengths of light, where you have short wavelengths, bluer light, and then longer wavelengths, redder light over here. And here's how bright the planet's atmosphere is at different wavelengths. You can see that there are strong signals of oxygen here and here, signals of ozone over here and here, signals of water over here, signal of carbon dioxide over here. And all of these signals are very obvious and very easy to find with an instrument as powerful as LUVOIR. So if a mission like LUVOIR were to launch in the 2030s, this would be our best bet to find alien life. We would be able to look at the atmospheres of rocky, habitable planets and see whether we can find biosignatures in those atmospheres and help answer the question of whether or not we are alone in the universe. So just to summarize, today I've told you about the radial velocity method and the transit method of finding exoplanets. I've told you about the Kepler mission, the K2 mission, the James Webb Space Telescope, and the proposed LUVOIR mission, and how these telescopes are used to find exoplanets today, and how hopefully in the future, the LUVOIR mission might be able to help us find signs of life in the atmospheres of other planets. So I'll leave this amusing XKCD comic up here, and I'll take questions from everyone. Thank you very much for listening to this talk. Thank you. Now, I'm having a little trouble pulling up the Q&A, but I believe I can swap over to another screen and show the Q&A. Here we are. So one question we have is, can there be planets made out of only liquid? This is a very interesting question. A planet like Jupiter, we know that the outer regions of the planet are gas, which is a fluid, but deeper down it becomes more compressed due to higher pressure and it becomes liquid. And some people are still questioning whether there's a rocky core at the center. So I don't want to say it's impossible, but I will say that it is a very hard thing to do. And I don't know whether there can be a planet made out of only liquid. Another question is, statistically, what percentage of stars with solar systems would be observable edge-on from Earth? So that's a really great question. That actually depends on how large the star is and how far away the planet is from the star. So if the planet is farther away from the star, it's less likely to transit. And if the star is smaller, then the planet is less likely to transit. But very roughly, the odds of an Earth-sized planet orbiting a sun-like star at the distance between the Earth and the sun, the likelihood of an Earth-like planet transiting is about 0.5%. So we need to look for a lot of systems to find an Earth twin. But for something like a Jupiter-sized planet orbiting a large star, like a hot Jupiter very close, the odds are much higher, maybe like 5 or 10 or even 20%. So it just depends on the system. Another question is, can there be large rocky planets? We think that once a planet gets larger than about 1.6 or so times the size of the Earth, then it tends to become more puffy. It starts to have a very large atmosphere. And we haven't found good examples of planets much larger than maybe 2 times the size of the Earth that actually have a rocky surface. So that's just because the larger the planet, the more gravity. And so it pulls on the atmosphere around it and is able to attract a more puffy atmosphere. Why is the mission called Kepler? Well, that is from the Johannes Kepler, the famous astronomer. Why that specific astronomer was selected, I do not know. We have a question about Kepler 62e, whether that is a habitable planet. That is one of the planets that was found through the Kepler mission. I think Kepler 62e, if I recall correctly, is a habitable planet, but you should consult Google to double check me on that one. I'm afraid I'm not 100% sure. Another question. If Earth-like planets are common, why hasn't SETI detected signs of intelligent life? That's a very, very interesting question. It could be because the way that aliens communicate is so much different from us that we don't know what we're looking for. It could be that they don't use radio waves. It could be that life is not very common. Or it could be that intelligent life is not very common. Maybe there are planets everywhere that have wildlife and greenery and forests and jungles and deserts, but no intelligent life like humans. Or it could be that life in general is extremely rare. And it just so happens that Earth is somewhat of an oddity. We don't have a good answer yet. What else? Do I believe there is life on different planets? I personally think it is very likely that there is life on other planets. And that's simply because in our own galaxy alone, there are over 100 billion stars. And we think that on average, there is maybe a planet or two at least for each of these stars. So we've got somewhere between 100 billion and a trillion planets. It just seems really unlikely to me that there's life on one planet here and no life anywhere else. What kind of alien life is being researched, and are we considering it alien because we've never seen it or because it comes from a different planet? So we have no evidence so far that there is life elsewhere besides Earth, but we also have no evidence that there isn't life elsewhere. What we are doing right now is there are some scientists that are making hypotheses, guesses as to what life elsewhere might look like. It might need to use sunlight like plants on Earth. It might be carnivorous, or it might be something that walks on legs or has fins or wings. So you can sort of make educated guesses about what life elsewhere might be like, and that can help you figure out what to look for. But we're not exactly researching alien life. We're more trying to guess what it could be like. Are there any Earth-like planets that have been discovered this year? Ooh, that's a very good question. I don't think so, actually. From earlier in my talk, I mentioned that there are currently 60 Earth-like planets in the sense that they are rocky and they are habitable. I believe the last time I gave a talk similar to this in 2019, it was also at 60. That's because a lot of those were discovered through the Kepler mission, and a lot of them were found very early on in the Kepler mission. So now that we have the TESS mission, which looks at stars for less time, it is harder to find small, rocky, habitable planets. But we do have other missions like the James Webb Space Telescope and other smaller missions that I didn't talk about that are going to continue to find more rocky, habitable planets. Have we found any exoplanets that have carbon? Yes, carbon is one of the most common things in the universe after hydrogen and helium, lithium, a couple other elements, but carbon is everywhere. Carbon makes up a large fraction of the planet Earth, makes up a large fraction of our own bodies. And if you, it's in rock, just regular old rock, there's lots of carbon. Graphite is carbon. So we have found evidence of carbon. Specifically, we found carbon dioxide, CO2, which is one carbon atom and two oxygen atoms. We've already used the atmospheric characterization method to find carbon dioxide in the atmospheres of other planets, as well as a number of other molecules as well. In fact, there's one planet that was discovered recently called K2-18b, where we found water vapor in the atmosphere of the planet. And that was a brand new discovery. We hadn't found water vapor orbiting in such a planet because that planet was also in the habitable zone. So that's very intriguing. Aren't we assuming that alien life needs water and air like us to live? Isn't it quite possible that they don't? I think this is probably going to be my last question because we're running a little short on time, but that is an excellent question. We want to make as few assumptions as possible about alien life. We know that life on Earth needs water and it needs oxygen or carbon dioxide. Plants need carbon dioxide. So we're trying to look for other planets that are very similar to our own, because if we make too many assumptions, one of those assumptions may be wrong, and we might be looking at a planet that can't sustain life at all. So we're trying to make as few assumptions as possible, but there are exoplanet scientists that try to break those assumptions and try to come up with other ways. Can we have life on a planet that's not rocky, or life that doesn't need water, or life that isn't carbon-based, but based on some other base molecule? And maybe we'll find life like that, but we also want to minimize the number of assumptions that we make. We only have a little bit of time left, so I just want to close by saying thank you, everyone, for all of your excellent questions. This has been a blast to deliver this talk, And I hope that I was able to answer a lot of your questions and tell you a little bit about how life can be found on other planets. So thank you very much, everyone.